Hi, this is Dan Bullard, retired electronics engineer, sitting on the front deck of Hospital again. Sunday, so we got a jet skier buzzing around over here, and plenty of boats going back and forth. Okay, this is part 6 of the Nextest DSP training course. We're going to talk about the FFT, and then we'll talk about DB, because DB can be a problem. Okay, to perform an FFT, in the code, use a function waveform real FFT. So you capture your wave. Here we did an ACI get waveform, capture 1, that's the ACI. Starting at element 0 and ACI wave, that's the waveform. Boom. So the data gets pulled out of the ACI, like when I did my Doppler shift, that was the microphone that picked up the train going by, ACI get wave. So it gets the waveform out of the ACI and puts it into a waveform. And then waveform real FFT, FFT wave, ACI wave. So ACI wave is the input wave, FFT wave is the output wave. And that's all you've got to do. Now in other testers I've used, you have to tell it how many samples you've got. But this thing looks at the samples you have and figures it out. Okay, things to know about the FFT. FFTs are very fast if you choose an N that is a power of 2. So if you do like 128 or 256 or 512, 1024, 65536, any power of 2. However, non-power of 2 FFTs work too, but they are slower by about 10 times. The software actually performs 3 radix 2 FFTs and some additional math. It's known as the Chirp Z transform. And I don't know anything about it. Daver wrote it. The other thing you need to know is the FFT produces a C-rect waveform. C-rect is that weird kind of waveform that I told you about. It's rectangular. It's complex rectangular. If you want it to look at the spectrum, you may want to convert to polar. Chances are good that you'll want to convert to polar. To get magnitude and phase, use a polar conversion. Say waveform rectangular to polar. Boom. It converts everything to polar. To get just the magnitude or just the phase, use the split function, waveform split. And then to rejoin split waveforms, use the join function, waveform join polar or waveform join complex. And to just get magnitude, use waveform magnitudes. Okay, here's a little example. Again, these are real examples. These are examples I wrote, and I compiled them and I tested them to make sure they work. So waveform real FFT, FFT wave captured. Waveform rectangular polar, polar wave, FFT wave. So FFT wave is the complex wave that came out of the real FFT. And now we've got a polar wave. Another guy went by. It's a nice day, so people are going to do that. People are going to go by. First, they don't have to throw a big wave. We don't have a problem. That's one reason we park Monaco style. Our bow is facing out. So that's the part that takes on the waves anyway when you're away. So he's throwing a big wave. Oh well, it rocks and rolls it a little bit. Okay, so we've done the rectangular to polar conversion. Now we can do waveform get element, polar wave, 63, that's the bin number, magnitude and phase. So we get element 63 from polar wave, that we get the magnitude and the phase. The next thing we do is we convert the phase into degrees from radians. Things to know about it. The magnitude is in peak amplitude. So if you want to calculate RMS, it's peak times 0.707. Now I told you about that. You can't use 0.707 all the time. There's a way. 0.707 works only for a single frequency, for a sine wave. But luckily, when you do an FFT, each bin is its own frequency. Each bin is its own sine wave. Every one. And so it's valid now to take whatever bin you did, in that case 63, take whatever bin you got and convert it into RMS by doing peak times 0.707. Remember that peak to peak is peak times 2. dBV is 20 times the log base 10 of peak over 1. And dBm is 20 times the log base 10 of peak divided by 0.3162. That assumes you're terminated at 50 ohms. That would be dBm. Okay, phases in radians. Degrees is radians times 180 over pi. And radians is degrees times pi over 180. Phase is relative to a cosine wave. That's important to remember. Sine waves will have an implicit minus 90 degree phase offset. So that's kind of important to remember. So when you do an FFT, the phase is relative to a cosine wave. That's why if you look at some of my examples, you'll see these minus 90 degree phases in there. Minus 90 degrees means it's a sine wave. Okay, we've done enough with FFTs. We beat FFTs to death. So let's talk about converting to dB. So dB is a unit based on ratio of two values. dB 20 times the log base 10 of V1 over V2. That's the definition. dB equals 10 times the log 10 of power 1 over power 2. Now, don't get confused. Voltage and power are different things. Power is voltage squared, remember that. So by taking 10 times the log base 10 of the ratio of two powers versus 20 times the log base 10 of two voltages, you're basically taking the square root. It's pretty cool. Okay, here's some common values. 6.0 dB, I talk about this all the time. 6.02 dB is 20 times the log of 2 volts over 1 volt. Okay, so that's kind of common. 6 dB we see all the time. 20 dB is 20 times the log base 10 of 10 volts over 1 volt. That is a factor of 10. We see that all the time. 40 dB is 20 times log base 10 of 100 divided by 1 volt. 60 dB is 20 times log base 10 of 1,000 over 1 volt. And 80 dB is 20 times log base 10 of 10,000 over 1 volt. So those are kind of easy to remember. A negative dB value indicates a ratio of less than 1. So minus 6.02 dB is equal to 20 times the log base 10 of 1 volt over 2 volts. Minus 20 dB is 20 times log base 10 of 1 over 10 volts, and so on. Digital devices are easy to figure out. Digital devices are based on powers of 2, where each bit is worth 6 dB. So 1 bit is 6.02 dB. That's 20 times log base 10 of 2 to the 1. 8 bits is 48 dB. 20 times log base 10 of 2 to the 8. 10 bits is 60 dB. 20 times log base 10 of 2 to the 10. 12 bits is 72 dB. 14 bits is 84 dB. 16 bits is 96 dB. That's CD quality. And 24 bits is 144 dB. So it's really pretty easy to work it out. I had a hard time early on figuring out how dB worked because I just didn't understand it. But now it's like second nature to me. Okay, in digital devices, the LSB is worth 1 part in 2 to the n possible states. In an 8-bit dot, or device under test, the LSB is worth minus 48 dB. That's 20 times the log base 10 of 1 over 2 to the 8. In a 10-bit device, the LSB is good for minus 60 dB. In a 12-bit device, the LSB is worth minus 72 dB, or 20 times log base 10 of 1 over 2 to the 12th. In a 14-bit device, it's minus 84 dB, and in a 16-bit device, like a CD, that's minus 96 dB. And then if you go 24 bits, and there are 24-bit devices out there, all Blu-ray players now have 24-bit analog, and you can tell they're horrible. When they're quiet, they're so quiet you can barely hear it. And when it's loud, it's so loud it's blowing the speakers out. So 24-bit, that's 144 dB. That's more than enough for everybody. Okay, to convert from dB to a ratio, use the following. 10 to the power of dB divided by 20. So 10 to the power of 6.02 dB divided by 20 is 2. 10 to the power of 20 dB divided by 20 is 10. 10 to the power of 40 dB divided by 20 is 100, and so on. That's pretty easy. To convert from dB to n bits, use the following. dB over 6 equals bits. So 48 dB divided by 6 is 8 bits. 60 dB divided by 6 is 10 bits. 72 dB divided by 6 is 12 bits, and so on. Again, there's the CD quality. Once you have the numbers in dB, products can be added and ratios can be subtracted. So for example, here's a waveform coming in very small. We go to an amplifier. We come in with 6 dB of gain. The waveform gets amplified a little bit. We go into another amplifier. It gets gained up again by another 6 dB. We go to another amplifier, gets gained up again by another 6 dB. We go to another amplifier, gets gained up by a factor of 2, that's 6 dB. So as far as the size goes, that waveform is 16 times bigger than it was originally. But in dB, it's plus 24 dB. So 24 dB is 20 times the log base 10 of 16. So that's kind of easy to work out. You know, I mean, long ago I had a hard time figuring this out, but it's not too tough. By the way, this sequence went into the Nextest book. Attenuators reduce amplitude, resulting in negative dB values. So here we have minus 24 dB is 20 times the log base 10 of 1 over 16. So a big signal comes in, we divide by 2, like using a voltage divider or something. So it takes 6 dB away. In other words, it divides by 2, makes it half the size it was. We go to the next stage, it divides it again. Go to the next stage, it divides again. Go to the next stage, it divides again. So divide by 2, divide by 2, divide by 2, divide by 2. We go down 6 dB at a crack. So the signal comes out 1/16 of the size it was. It's minus 24 dB. Be really careful when doing program conversions. That was kind of advice to my students, because some testers see rect polar conversions spit out the voltage in peak squared. So that was an issue. Now, David did that early on in the STS 3000, because the array processor, the thing that did the math to do all this stuff, it was really tough. It was really hard, and he wanted to make sure he got the most speed out of it. Since most people were going for voltage squared so they can get dB in power, he just left it volt squared. So dB is 10 times the log base 10 of V1 squared over V2 squared. If the voltage is already squared, you don't have to use 20 times, use 10 times. So that could be a real issue for some people. So multiplying by 10 instead of 20 is the same thing as taking the square root of the ratio before converting to dB. I know sometimes this math stuff gets to be an issue. So in logarithms, adding results in multiplication, subtracting results in division, multiplying results in raising to a power, and dividing results in taking the root. So you got to be careful there. And then a final word on dB. People got really upset with me when I talked about this back at Nextest. Never misspell dB. Never misspell dB. And you say, Dan, how could you misspell dB? It's only 2 letters, D and B. No, 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 no. It's lowercase d, uppercase B. That's named for a guy named Bell. Remember Ma Bell, the Bell Telephone Company? Ma Bell. It's spelled with an uppercase B. So it's always lowercase d, uppercase B. if you're talking to an analog engineer and you use a lowercase d and a lowercase b, or an uppercase d and an uppercase b, they just assume you don't know what you're talking about. So that's important to remember. You don't want to sound like a complete fucking idiot, you know? Okay, so next up we're going to talk about DACs, and then after that we'll talk about ADCs. So this is pretty simple stuff here, relatively. So once again, from the river, this is Dan Bullard. See ya.